Thanks for being here at my presentation, seeing this new presentation that I'm going to try on you, so let's see how it goes. We'll try to tame some of the effects of distributed computing using types. That's the basic promise here. So, what is this thing, this distribution? Who here thinks they have a really solid grasp on what distribution means? So distributed computing, who could, I mean, I'm not asking you to, but raise your hand if you would be able to describe it. Yeah, okay, of course you do. People know basically, I mean, most people will probably have said, yeah, distribution is hard, but that's hardly a definition. So we need to be a bit more precise here, because we'll tackle one of the aspects and leave the others alone. So this distribution here, for this purpose of essentially why it's hard, I would like to decompose into two parts. The first part is if you have distributed components that run on distributed hardware, on EC2, different nodes, and so on, you inherently have concurrency. You have things happening at the same time. You have processes running, and this one makes progress, that one makes progress. So far, so logical. But that is not only the case if you run in the cloud on different nodes. It's also the case in JavaScript, for example. Even if you don't use web workers and anything, you have a single-threaded runtime, you still have concurrency, because concurrency means I have this process that is going to, from here to there, so it's going to calculate something from these inputs, this output, and I have another one that's going on basically with an overlapping time interval between start and end. And with JavaScript, it might happen that the execution is going back and forth between these two. When one yields, the other runs, and so on. This is also concurrency. This is hard. We'll talk about why it's hard in a second. There is a second part. As soon as Aaron has talked about that in the previous presentation quite a bit as well. When you have a distributed system, well, things can fail. I mean, things can fail anyway. Yeah? Your computer can just fail, and then you're sad, especially if it happens during presentation. That would be bad. Or your database server goes down. You have only one that's really bad. But if you have two database servers and one of them fails, that's a new kind of bad. It's an entirely new level of badness, because now you cannot really distinguish, do I have a network partition so one just can't talk to the other, or is the other one really just, for example, fuse blue and it's out of power? You cannot really make that call. And on the other side, if there is a network partition, you cannot make that call, really, and you can get into these split brain situations and scenarios. So partial failure means that a part of your system can fail, but that doesn't mean that the whole system fails. Some parts of the system stay running. This is very necessary if you want to model what it means to be distributed, because, I mean, that's just what the world is. In this sense, actors form a very precise model of what it means to be distributed. Actors are isolated. They can fail for themselves. One fails, the others are not impacted. They can make progress concurrently. In parallel, if you have multiple processor cores available to you, but only within an actor you have sequential processing of the messages that come in, but between actors you have concurrency. Actors, as I recently found out and wrote a blog post about, I mean, I was probably not the first to find that out, I write that as well. Most of this has come from the 70s and 80s, but actors very accurately model what it means to be distributed. That you can only communicate via immutable message passing, and you react to messages and do these three primitive actions: creating actors, sending messages, change your behavior. It's a very minimal model that precisely expresses what it means to be distributed. It has no fluff, and it lacks nothing in that regard. So, we were going to talk about some of the problems, some of the hard parts. Well, one part is concurrency already implies non-determinism. If you have two processes that go on with overlapping time intervals, then the ordering of things that they do in the meantime, the effects that they produce, for example, there is no inherent ordering to them. If you try to observe them from the outside, for example, you write a test case, and you run this program that consists of two concurrent parts, you might get the messages that come out of these two parts, or the results, or the side effects. In the test procedure, you might get them in any order. I mean, not really any, we'll talk about restrictions, but there will be aspects that are not defined, that are not a priori given. On the other hand, if we look at, for example, an e-commerce site, non-determinism is very much needed, and we are all very comfortable with, first of all, making use of it and programming for it. Because nobody knows when they write the program who will order what goods at which time. The world is non-deterministic as far as we're concerned. Our programs don't know, especially the server processes, don't know in which order the requests will come. There is a lot of non-determinism that we're completely fine with. It's just that we don't really like it between lines in the program. We want to have our islands of sanity inside this sea of non-determinism. Well, I mean, that's also what actors provide you. The second one, well, distribution makes it even more non-deterministic. I talked about the partial failure. We have completely new modes of things that can go wrong. And they are not determined up front in any way. So this is really, really hard. Non-determinism in these tests usually means that you write test suites that need to run not only the system under ideal conditions, it also needs to run, for example, the Akka cluster implementation has lots of tests that trigger node separations and so on, network partitions, data message loss, what have you, in order to figure out, do we have any conditions in our code that somehow then cannot deal with a certain failure scenario. These tests are very hard to write. You need to write them such that they actually cover all the bases, which you will learn you never do. You just always add one when you know that you've forgotten it. And they also take a long time to execute. Your Travis jobs will run quite a bit longer if you don't have the luxury of deterministic testing. You need to run lots and lots of stochastical tests, and they might take a lot of time. So we want to really restrict this non-determinism a little bit. That would be so cool. There is a tool. It's built into nature itself. It's called causality. Causality restricts the kind of non-determinism. So it makes certain things ordered. As a very basic example, so some of these causality comes very naturally. If I ask you something, you may respond, but you will not respond before I asked you because you didn't know that I would ask. The same goes for computer systems. As long as I have not sent the request message, well, it cannot possibly have been received, and I cannot possibly get an answer to that yet, because I haven't sent anything. So there are certain things that are excluded. There is still non-determinism, but there are bounds to it. And these bounds sometimes come very naturally. We can exploit that. Here is some, so in Akka Typed we use messages to describe protocols. ActorRefs featured in the previous presentation already. They are handles sending messages via ActorRefs to actors. So this describes a little protocol. This Receptionist is a piece of API through which, it's like a service locator, you could call it that. And the first part here is the register message that someone who wants to advertise the fact that they speak a certain protocol that they send to the receptionist. When you send a register, you include an ActorRef reply to, ActorRef of type registered. So the receptionist will respond with a message called of type registered. So it's a simple game. You send a request register, you get a response registered. So clear. And one cannot come. One can only come after the other. That's natural causality here. The same goes for the find operation in response to which you get a listing. Now we can push that a bit further to illustrate a few finer points. I can add something here, a feature. like if I wanted to unregister. So in this registered message that gets sent back as a confirmation, I now have another handle. It's an ActorRef of type unregister. And whoever gets this now holds the power in their hands to undo this registration. But one thing, the funny thing here is, this is not part of the public API. Yeah? This unregister does not extend command, so you cannot send it to the receptionist just like that. You don't have a handle by which you can send it to anyone until you got it. And when you got it, this handle, this ActorRef of unregister, could be a very specific one. The receptionist could give you, could create a new actor only for you, representing your registration. And then when you send the unregister, only you can unregister your very self and no one else. So you can express lots more safety once you use these message types to model protocols. And of course, causality, first register, then registered, then you can potentially unregister, and only then can you receive the unregistered. This can only happen in this very sequence. It cannot happen in any other order because of the laws of physics, essentially. Now, these are the things that are fixed by causality. But if you look at this API, you note I could send either a register or I could send a find, because they are both commands. And this is non-deterministic. So not everything is restricted here. In general, for everything that is not restricted by causality or other means, you need some form of coordination. Otherwise, you still have non-determinism. We talked about shopping carts, e-commerce. Not everything needs to be deterministic, but the things that you want to be deterministic need coordination unless they are fixed by causality. Coordination is very costly. Who here listened to Kyle Kingsbury's Jepson talk this morning? There is a reason why he finds all these bugs or documentation features for certain databases, because making sure that everything is consistent has a cost. It has a very high cost, both in terms of complexity of the implementation, but also, more importantly, in many cases, in terms of runtime performance. You need lots of communication between the parts of the system to achieve this coordination and then thereby achieve consistency. Now, there is one thing, one very, very elegant way you can eliminate the need for coordination. It's basically also causality. If the thing you use has been clear before the program starts, static knowledge. Well, that was before the program started, so everybody can know it. There's no need to coordinate. It's just a fact that you can use. Now, this is very useful. It might sound trivial, but it's very useful. I'll give you an example. This receptionist currently does not have clustering capabilities. It doesn't have any connection to the remote subsystem in Akka because it's still in beta mode, so to speak. But it's pretty clear how this can be extended to be a cluster receptionist. A cluster receptionist would be one, you have a receptionist at every node. And if you want to obtain an ActorRef for a certain protocol, you ask your local receptionist, and it will know if that protocol is spoken anywhere in the cluster. And if it is, then you get back an ActorRef for that protocol. Yeah, so far, so clear? Okay. Well, we need to coordinate sort of the lookup names, how you find these other actors by naming their protocol. And if you use, for example, the fully qualified class name of a service key, that is, I had this trait on one of the slides, a service key is just parameterized by a type T of the protocol, and it's an object, a singleton that you put somewhere in the source code, and the only purpose of that is to get a fully qualified class name that you then manage as you manage source code, such that it can exist only once for a certain type. Because that's what we're good at. We use packages and so on. So the names that we use are coordinated before. And this is why the cluster receptionist can use this to communicate, okay, I get the service key on a local host. I just need to transmit the fully qualified class name to all my peer receptionists to try and look for a suitable suitable implementation of the protocol, because they agree on this. It's static knowledge that was known beforehand. The local resolution then makes use of this parameterized singleton object. The static type checking, no matter whether you use C#, it would work there as well, or Scala or Java. This all makes sure that the local resolution will give you an ActorRef of the correct type. So this works. And then for Chris back there in the room, I think it would be very nice to use CRDTs to manage the knowledge that all these receptionists share, because in the end, it's just a map from protocols to a set of implementations, and I mean, it doesn't need to be linearizable or anything like that. It doesn't need to have a zookeeper behind it. This just needs to eventually learn of who is where. That's good enough. So that will be a highly available cluster receptionist for Akka that can give you type safety. So, I mean, this was just a small excursion. Now, coming back to causality. Causality fixes a few things, but it doesn't fix a few other things. As I said, this protocol that we looked at has 2 entry points, and you don't know which one the client is going to choose first, for example. So, natural causality is not enough. We look at another example that might seem a little less construed, I hope. Payment with an audit. So let's define some messages for a payment system. First, we take the audit service. There is a service key for it that demonstrates how you would do that in Scala with Akka Typed. Then you have the 2 messages, a log activity message and an activity logged message reply that confirms that the audit log has been done. Nothing fancy so far. Case class is just, who here can read Scala? Yeah, okay. Case classes are so handy on slides. Okay, then we have the payment service. I mean, this is just a sketch of a generic payment gateway, so to speak. It has 4 operations. You can authorize a certain amount for a certain payer. You can capture an amount that has been authorized previously. You can void a transaction, or you can refund a transaction. So these messages all have a reply to field of type ActorRef of payment result. Payment results, I mean, in reality, this would be much more complicated. But payment results we consider here are success, rejected, or ID unknown. So given these messages, we could implement an actor. So who here knows Akka Typed? Yeah. Who here knows Akka on the JVM? Okay, so we'll start with that. This is a very simple greeter actor, classical untyped Akka. So greeter extends akka.actor.actor. You only need to define the initial behavior, def receive, which is a partial function which pattern matches on the greet message. Just for conciseness, I use Scala syntax. I like that very much. And then we print line the hello with string interpolation. Now, translating this into Akka Typed is not that different, only there is no actor to extend from. Because in Akka Typed, we only deal with the behaviors. The actor is a concept, that's clear, but in the end, also in the untyped Akka, it's nothing more than you have a current behavior, and you have the next message, you put the message into the behavior, and out comes, well, the next behavior. That's what Carl Hewitt said in 1973, and that's how it's implemented in Akka Typed. There are constructors for these behaviors. You can see here actor.immutable. Immutable means this piece of behavior itself does not feature any variables in it. If you want to change the actor's state, you can still do that. You just need to return a different behavior after processing a message. In this case, we don't do that. We just print line hello world or whatever, and then actor.same says, okay, stay in this behavior and keep doing what you were doing. So this is a greeter. So far, so clear? Okay. So let's implement the audit and then the payment. So first, the audit. First, we define some confirmation messages, audit done and payment done, so you're not surprised when you see them. Now, doAudit is a method that returns the behavior of an actor, and this actor needs to do something before it waits for a message. That's what actor.deferred is good for. Actor.deferred describes a behavior. In this case, it can receive activity logged, which we will want to do later. But first, we use random next long to generate a random ID, use that to create a log activity message, send that to the audit service. Now we need to wait. We don't want to wait forever. In distributed systems, you never want to wait forever. That's a really bad idea because, I mean, the other thing might just die and then you wait forever. So there's a timeout. Well, this works on a slide. It's slightly odious. I mean, there's a null in there. One could have done it in different fashions, but this is the most concise way. In Scala 3 or .t, we would get union types, where we could then make this actor type one that can receive activity logged or receive timeout. That would be very interesting. It's not possible right now. So now we just schedule in 3 seconds to context.self, so to ourselves, an activity logged with this null in there to say, okay, this was not actually a successful confirmation, this was a timeout. Now, then we install the immutable behavior that looks at this. So if message.who is null, it's a timeout. Otherwise, if the ID doesn't match, it's invalid. And otherwise, well, someone was interested in this. That's the who parameter. And that one gets now the confirmation that the audit has been done. And we stop this behavior. Returning actor.stopped means that this actor will be garbage collected and is gone. Will not be scheduled anymore. Cannot receive any messages anymore. Okay. Now we do the payment. Doing the payment is one step more, basically. It's the same process. We use actor.deferred because first we need to send the authorize before we wait. Same trick for the timeout in this case. Then we install a behavior that when the payment success comes back for the authorized message, we send the capture to actually get the money. Again, return a behavior that then waits for payment success. And when that has happened, we send back a payment done and stop the actor. Yeah? So this actor is just a tiny process that does a two-step exchange with the payment service. So now we have implemented all the pieces, we can put them together. Orchestration of the process. It's the same principle over again. Only what we do here is we don't really send messages ourselves. We use the processes that we have defined so far. So we use context.spawn on these things, do audit first, and then do payment, and then do audit again. We use context.watch on every of these results because we want to know when they fail. If one of these actors fails, then this one will get a signal with the failure and will fail as well. Now, this is a very simple let it crash philosophy approach. You could be more sophisticated, of course, do a rollback, what have you, but this works. This informs also whoever has started this, so the parent of this actor will then also see, okay, this has failed. Yeah. So, I mean, it's a ladder of these steps. So we do the audit. When the audit done comes back, we do the payment. When the payment done comes back, we do the audit. Audit done comes back. We're done. Finished. Yeah? That's very nice, isn't it? I mean, it looks a bit like the Pyramid of Doom. And the microphone. It works again. Yeah, so there's lots of uncertainty in here as well. We have not really conquered the non-determinism yet, so to speak. Because, I mean, I could have mistyped and done the payment after the last audit, for example, and the type checker wouldn't have told me anything. It would have been completely legal code to first do the both audits and then do the payment. Or I could have forgotten the second audit. If I leave it out, the Scala compiler will not tell me. It's just on me to remember what kind of things I need to do. So, can we do something about this? And that's what this talk is getting at. Yeah, can we fix these problems that we employ knowledge in the wrong order, or that we forget to employ knowledge that we have learned? Well, what if we could prescribe the effects that happen? Because that's what we care about. What if we could tell the compiler, okay, check for me whether I send these messages and whether I wait for these kind of messages. That would be so cool. So what do we want to do? Which steps shall be done? We want to send an audit log and get confirmation. We want to send the authorized message, get confirmation. Same for the capture. And then we want to do an audit log again. How can we write that down in the type system? Because that's what we will need to do. And this is where it gets a bit funky, and that's why this talk is an advanced one. Because, well, this is a Scala type signature that is on lots of lines. Normally, type signatures are much shorter. And one of the problems here, I'll talk about that later, is also error reporting. I admit that. So, this is a transcription of the process. Yeah? This colon type in there is an infix type notation for a cons of an HList. Who here has heard of an HList? Heterogeneous lists or lists on the type level. It's a type that has two parameters, a head and a tail, which is a list again, and so on. And there is a nil for that, an empty list, which is the _0 that you see here. Now we build a list of types, essentially. The first one is sending log activity, then read activity logged. These are types, not values, right? And then comes a funky one. You'll see where that comes from when I show the code that does it. We have a choice here, because, well, we send log activity, we get back activity logged. What if the response doesn't validate, has the wrong ID in it, for example? Well, then we would terminate the process. That's what this choice expresses. Choice means, in there you have the colon plus colon. This is an OR. Now, the other ones is a second. This is an OR. So either we halt as an effect, so we stop the process, or no effects, so it goes on. And this goes on for every step. So authorization gives a payment result, capture gives a payment result, log activity gives an activity logged. Every time we check whether the result was as we wanted it to be, terminate, if not, continue otherwise. So, this is a type only. Now we need an implementation for that. We need to write something down that does the process. That's the second half, and we need to bring them together. And this is where this Akka Typed session project comes in that I have started developing on GitHub. The code here is from that. It has this op-DSL, operation DSL. It consists of operations that typically have effects. An operation is op-send, sending a message, obviously. First you give the target, then you give a suitable message that you can send to that target. Depending on the types, it will all be checked. Op-read reads. Now, each process, that was one realization. I had something inspired by PyCalculus tried out first, where you can read on channels to collect the messages from where you want to read them. This turned out to be not so good. There's another blog post that explains that. Basically, it's safer in a distributed fashion to use the fact that the actor model so completely models what this means. So this process is like a mini actor. And it has one ActorRef for itself through which messages can enter this process and none other. And this also needs a type. And that's what you see, op-DSL of activity logged in the top left that describes, okay, I'm formulating a process here whose self-reference is of type activity logged. And then you can use op-process-self as an operator to get access to this address. And then you can use it. Now, this all is in this very handy for expression. A for expression is basically syntactic sugar. It's a Scala thing, which lets you condense code that would normally be for example, with promises, it would be a do something, dot, and then do something, and then do something. Yeah, you've seen that to get rid of callback hell or a pyramid of doom sort of thing. You switch to promises in JavaScript. Well, I mean, this is the same thing. It just Scala has special syntax for this sequencing with the and then. The and then in Scala is called flat map, but that's a technical detail. So this op process self is a thing that has a flat map method, and then you can chain these operations together. So when everything is said and done, so when the op read has returned a value, each of these processes returns some sort of value. This is deconstructed with a pattern match. To the left, this left pointing arrow points at the activity logged over there. This is a pattern match that says, okay, I know it's an activity logged because type safe actor references and so on, but this also says, okay, the first parameter in it must be literally the who parameter. If it's not, fail. The second one must be ID. If it's not, fail. And if everything goes through, then we yield done. Yeah? This pattern match gets translated into a filter instructions. A filter instruction. You also know that from Java Extreme. Yeah? You can map, you can filter. Well, filter is what this gets compiled down to. Okay, so this creates an operation. And then I say dot with timeout 3 seconds. The interpreter that runs this process eventually, I mean, this is the description of a process. It doesn't run when you execute this method. The process gets returned, and you can compose it and so on, and sooner or later you put it in an actor, which is an interpreter that runs it. This interpreter then takes note of this timeout, and if this is still running after 3 seconds, it will fail. A failure will be introduced, just like for the actor solution. Now, the interesting part is the return type is a process. So that's what happens when you define the timeout. Operation gets into a process. Its self-type is activity logged. The result type is done, and then you see the effects. The effects that are accumulated while constructing this thing. So this sends something, reads something, then has the choice from the pattern match. Is that clear? I guess this is a mouthful to digest, but yeah. So here is the payment, which is basically just the same thing again, just one step more. Yeah, different messages. Another send and read loop, so to speak, that we take. And the type that is returned consequently also captures this. We do the send, read, and choice part 2 times. Okay, so we have these 2 methods defined that can describe the process of doing an audit log or the process of doing a payment with this 2-step process. Now we need to orchestrate them. Yeah, we need to put them together. Well, there is another process that we are going to use, get service, because we can describe processes. We know how to talk to a receptionist, and part of the library is this get service thing that knows how, given a service key, how to get a listing of ActorRefs. So that's what we use here. Then the get money description of a process turns into just this sequencing of steps, where you note there is a new thing, op-call. Yeah? So I can take a process, a sub-process that I have defined with a certain self-ActorRef type and so on, and call it. Call it exactly like I would call a method or a function. Yeah? It runs in its own stack frame, in its own execution context. It runs in the same actor, to be clear, but it's a separate process that has its own input channel, so to not confuse things. So we can first do the get service that will speak to the receptionist, get a result. Then we do the audit that will speak to the audit. No one else is disturbed, right? And this is done. Do payment, also the same thing. They're all decoupled. And once everything has completed successfully, we send back the reply to a message that whoever spawns this process wanted to have. Now the funky thing here, and I'm still so excited about it, is that, well, this type, of course, also captures all the effects that are in here. They are accumulated. The type is a bit too big to put it on this slide, and you've seen it in the objects of the protocol before. But what you can do now is you write a method. Yeah, you don't ever have to call this method. You just write this method, private def verify, which uses a function vet external protocol from the library, where you get put in the get money protocol object that has this type in it, this sequence of steps that are expected, and you call get money, yeah, which has a certain return type. And then the compiler looks at the get money protocol's session description. It looks at the return type of get money, and does a type-level computation to figure out whether one is compatible with the other. Clear? So this would give a compile time error if you would delete one of the lines in there, because it would say, oh, you forgot to send this audit log, for example. It would clearly flag that. Well, there's a to-do here. Yeah? Clearly, as in it doesn't compile. And if you really understand how Scala reports errors, then you can read it, but it's kind of like a C++ template level error reporting. So this really needs to be a macro. And if we make this a macro instead, then we can have nice error reporting. It's only a macro for the purpose of error reporting. Do we take that afterwards, or? Okay. Because, I mean, I'm a bit too fast, possibly even, because this is already my last slide. No, I have 2.5 minutes. Okay. So the conclusion is, I think there's a lot on the table here. We can do a lot of things. We can capture what an actor is supposed to do that is necessary so that we can hook up the overall plan of how our distributed system is going to work together. We have lots of components in there and so on. There are ways for describing the protocols that are spoken among the components such that a computer can evaluate them and check whether the protocol itself makes sense, first of all. And if it makes sense, so if the protocol ensures that no party gets confused in the process or gets stuck in the process and so on, then we can emit the descriptions for what every participant has to do. And we can emit them in the form of these types that you have seen, and then whatever you implement your actors with, it can be checked that it does conform, it does its part. And I think that is very, very interesting and needs further development. There's a GitHub project, so please do get involved. And yeah, thanks a lot for your attention.
Thank you, Roland. If there's any questions, please put your hand up and we'll bring over a microphone.
So there's two things that confuse me on the last slide. Not this one, but the one before that. And one is, so the get service on the audit service, that one doesn't end up in the type signature, or does it? Because otherwise we would have to put that in the protocol as well, and we don't really want to do that. That doesn't really...
Yes, okay, exactly. There's a trick here that I glossed over. So get service returns an operation. Self-type is listing of T. It returns an ActorRef of T. And it does not have any effects, the _0, because there is something you can call on these processes, which is called .ignore effects, where you can say, okay, these are internal effects, don't care about them. It's on you if you do that, but I mean, here it's very useful. It's an internal communication inside the node, shouldn't be observable, and so on. By the way, that is one of the big challenges. That's one of the problems. If you have an actor that speaks with multiple parties, you need to really separate out the piece of the protocol that belongs into this global session that you want to verify. And it might even be part of 2 of such sessions. This is why the operations DSL can also run things in parallel. You can fork, and then your actor basically has 2 parts on the inside, one speaking that protocol and the other speaking that protocol. But that is one of the questions that has not yet fully been answered, how well that works in practice.
Thanks. And the other thing is, why do you have to call that external protocol? Couldn't you just annotate the get money method with the types, saying
yes.
This is of type get money protocol, and then
that's
the same thing? Okay.
Yes, sure. But this will, I mean, we could also use an annotation on it that calls a macro in Scala. That's possible. What I would prefer is that, so this get money protocol object that came from, let's put that on again. That came from here. Now, this object is supposed to be generated by some automatic process. So I want to include that. That was one of the purposes. You could use that type and say this is get money protocol .session. Yes, that's true.
Thank you.
Any other questions for Roland? If not, we'll leave it there. And again, thank you, Roland.
Thank you.